Today we will start our next unit, that is limit state of collapse. So in this unit now we are going to design the singly and doubly reinforced sections. Okay, so we are going to design the singly and doubly reinforced sections over here. So we will see first the theoretical part of this, what is the singly reinforced section. Then we will move forward. In this, you should learn three types of sections. That is under reinforced sections, balanced section, and over reinforced section. So one by one, we are going to see that what is balanced section, what is under reinforced section, what is over reinforced section. You might remember the things in first lecture. I have we have drawn some diagrams. Okay, the diagram will be, it is I think so, like this. So diagram is this stress profile. Okay, here, and here we have shown this is the force Cu, this is the force Tu. Okay, we have also calculated the values of this. We have shown that this is acting at a distance of 0.42 xu. Okay, and xu is nothing but what it is, depth of neutral axis. Okay, all these things we had studied in the first lecture. So we will recall these things now. The Cu is the compressive force, Tu is the tensile force, and the distance between these two forces, this is called as lever arm, Z. Okay, so in this singly and doubly reinforced sections, we are using these to calculate and to analyze the sections. Okay, so further if we see, I will erase this first. Okay, so now we will start with the definition. What is the singly reinforced section? So I will write the definition of singly reinforced section. Before that, we will see what is limit state of collapse. Okay, so we will see. I will take this at the bottom. So here I will write this first, limit state in simple word. Okay, limit state. Side by side you take down these notes. So now limit state is nothing but it is limiting value of member. This is nothing but limiting value of member, limiting value of member to carry out stresses. Okay, to carry out stresses. This is the limiting value of member to carry out stresses. That is what is the meaning of this limit state method. Okay, so now after this limit state, this is in short I am writing. What is the limit state? Limiting value of member to carry out the stresses. What will be the limiting value of the member? That describes by the limit state. Then next is collapse. Okay, the meaning of word collapse. What is the meaning of collapse? So collapse is failure of member. Collapse is nothing but failure of member. Okay, collapse is nothing but, sorry, collapse is I will write here. Collapse is nothing but failure of the member. It is the failure of the member due to due to it is due to excessive stress. It is due to excessive stress. Okay. Or you can also say load. The failure of the member due to excessive stress or load is nothing but collapse. And if you combine this limit state of collapse, then we can say that, okay, if I combine now, if I combine over here limit state of collapse, okay, limit state of collapse, so I can write before that I will make some space over here. Okay, so limit state of collapse we can write combinedly. It is limiting value. It is limiting value of member. It is limiting value of member to to avoid failure failure due to excessive load due to excessive load or stress. Okay, so limit state of collapse means it is the limiting value of the member to avoid the failure due to excessive load. So now after this, now we will come to this singly reinforced sections. Okay, so we will see what are the singly reinforced sections and how do we define the singly reinforced sections. Now if I write down the definition of the singly reinforced sections, then it says that the section in which the reinforcement is provided on the tension side is called as singly reinforced sections. Okay, so I will write the definition. You also copy the same definition. Singly reinforced section, the section in which is the section. Okay, it is the section in which reinforcement is provided. In which reinforcement reinforcement is provided. Reinforcement is provided on tension side. On tension side is known as is known as singly reinforced section. Is known as singly reinforced section. Okay, as I have already told you, if I draw the shape here, see, this is our rectangle. Now, uh, this axis, this axis is our neutral axis. Okay, so this axis we call this axis as a neutral axis. Neutral axis. So the normally, if you see any beam, now if I draw the beam over here, if you see any beam, then normally the beam is supported. It is in this way, and it is suppose the supports are provided at the ends, and any arbitrary loading is acting on the beam. This is the loading. okay, W, any arbitrary loading, then this beam will deflect. Okay, then the deflection of this beam is like this. Okay, this is the sagging, we can say. This is the deflection. This is the deflection profile of the beam. Okay, and then we draw the neutral axis again here. So this may be our neutral axis. And what we assume that every fiber or element on the neutral axis is not undergoing any force. Okay, so the force on the every fiber or every molecule which is present over the neutral axis experience zero force. That is our assumption, and that is why we call this as a neutral axis. Okay, so if you see that here the compression is there above the neutral axis, below the neutral axis tension zone is there. Same thing is there in the beam. Okay, so above the neutral axis, if you see here, this is called as compression zone, and this is called as tension zone. Okay, so this is called as compression zone, and this zone is called as tension zone. Now, why I have drawn this diagram? Now, to understand the definition, the section in which the reinforcement is provided on tension side. Okay, the reinforcement, where the reinforcement is provided, it is provided on the tension side. Okay, see this. So now here, if you look tension side, this is the tension side. So if the reinforcement provided below the neutral axis, then these types of sections are called as singly reinforced section. So only the reinforcement designed for the tension. There is no reinforcement designed for the compression. Okay, concrete is sufficient to take care of the compressive forces or compressive stresses, but for the tensile stresses or tensile forces, a special reinforcement is provided. That is, we design the reinforcement. So these types of sections are called as the singly reinforced sections. Okay. Now after this singly reinforced sections, we will see the moment of resistance. Okay, moment of resistance for different grades of steel. So our next heading will be moment of resistance. Moment of resistance. Now for that, I will draw one table over here. So now this is our table. So I will give heading over here. So first, here in this table, I will write grade of steel. Okay. Here it is the grade of steel. Then here it is XU max value. XU max, so maximum depth of neutral axis. XU max value. Okay. And then here the moment of resistance value. Moment of resistance, or this is also called as limiting moment of resistance or limiting moment. MU limiting. Another name for this is MU limiting. Now if we see grade of steel, if we take for Fe 250, if we take for Fe 250, then the value of XU max is 0.53 D, where D is the effective depth of the section, where small d is the effective depth of the section, and the moment of resistance for that, it is 0.149. We are already using this in the slab FCK BD square. Okay, this is for Fe 250. Now if we go for Fe 415, for Fe 415, this value of XU max, the value of XU max is 0.48D. All these values are given in IS code. I will also show you in the IS code. So this is 0.48D, and it is moment of resistance for this is 0.138 FCK BD square. This is the moment of resistance. And now the last one, Fe 500. Okay, Fe 500. For Fe 500, Fe 500 it is 0.46D. It is 0.46D, and this value is 0.133 FCK BD square. Okay. So you copy down this table for different grades of steels, the different values of X2 max and the moment of resistance or MU limiting values. These values we have already used by designing the slab. Still, you note down this. Okay, 0.149 FCK BD square, 0.138 FCK BD square, and 0.133 FCK BD square. Now we see these values 0.53D, 0.48D, 0.46D. Where do that come? So we will go to the IS code then. Okay, so now we will go to the IS code. See here now. If I now see here, these values are given. This is the grade of steel, and this is the XU max by D ratio. This is the XU max by D ratio. If 250 is there, the ratio is 0.53 for Fe 250. For Fe 250, what is the value of XU max by D? So if I write over here XU max upon D, this value is given as 0.53. So this value is 0.53. Okay, this value is 0.53. If this value is 0.53, then I can write XU max. What is the value of XU max? XU max is equal to 0.53D. XU max is equal to 0.53D, where XU max is the maximum depth of neutral axis. Okay, and D is the effective depth. Similarly here, for Fe415, okay, for here Fe415, what is the value? 0.48. For Fe415, we can write XU max is equal to what? 0.48D. Okay, so Fe415, we can write XU max is must be equal to 0.48 times D. And for this now Fe500, what is the value? It is 0.46. So for Fe500, we can write XU max is equal to 0.46. So all these values are given in the IS code. It, there is no necessity to by heart these values or remember these values. Here on the page number 70. Okay, page number 70, these values are given which I have shown in the table, but the moment of resistance is not given. That value you should remember. The coefficients at least you should remember. We know that FCK BD square is the common term in the moment of resistance calculation. This FCK BD square is common. Just we have to remember the coefficient. So 0.53. So this 0.53 the coefficient is 0.149. So 0.48 the coefficient is 0.138. So this is 250. For T250 coefficient is 149. For Fe415 coefficient is 0.138. And for Fe500, what is the coefficient? It is 0.133. Okay. And FCK BD square, this term is the common term. So here the formula for moment of resistance becomes for Fe250 is 0.149 FCK BD square. Likewise, you have to use this formula. Okay. So now we will go back to our presentation, our slides. One more. So here, this table is now in front of you. So I hope you have copied down this table. Now we will see how the forces are acting and all those things we will see now. So I will draw here one diagram now. Rectangle. So this is the rectangle. Now I will draw the neutral axis. This is the neutral axis. Okay. So this axis is the neutral axis. This is the neutral axis. So now I will project these lines forward. Okay. If I project these lines, now we will draw here the strain distribution first. Okay. Now if I draw the strain distribution, then it is like this. So this is the straight line first. Now again Again, we will draw strain distribution diagram, which we have already seen. Here also we need to draw the strain distribution diagram. From this strain distribution diagram, we will draw the stress distribution diagram also. Side by side, you also draw this diagram with me. Okay. So again now, from this may be the diagram. Okay. So this is strain distribution diagram. Okay. So this diagram is the strain distribution diagram. Here it is your neutral axis. Somewhat from this point your neutral axis is passing. Okay. So the strain, this is the compressive strain. This is plus. Here it is the tensile strain. It is always minus. So the compressive strain, it is the maximum value of compressive strain is, it is 0.0035. Okay. And the tensile strain, it can be calculated as 0.87 Fy divided by ES. All these are formulas. Plus, and all these details are given in IS code 0.002. So this is your strain distribution diagram. This is your strain distribution diagram. And if I take this part little more further, if I project this neutral axis, so to draw the stress distribution diagram, okay. Now suppose that the reinforcement is provided in the beam, the reinforcement is provided in the beam here. Here the reinforcement is provided in the beam. Okay. Here these are the steel bars. This is the reinforcement which is provided in the beam. So again, if I project that reinforcement also, if I project this line of reinforcement where the tensile force is acting, here at this point the tensile force will act. Okay. So I will project this line also. Now we will draw the stress distribution diagram. So again, I will draw the line again. So here this is the straight line. Then straight to draw the stress distribution diagram. Here is straight line again. So it is up to some point again it is straight line. We have seen this curve already. Okay, and from this point it now becomes parabolic. This is the stress distribution diagram. Okay, this is the stress distribution diagram. So I will draw this curve. Okay, this portion is the straight line portion, and from here your parabolic portion starts. This we have already seen in the first lecture. Now if I draw the compressive force will be locating somewhere here. This is the compressive force. We give this notation to this force as a Cu, and here at the level of this reinforcement, the tensile force is there. This tensile force, we call this force as a Tu, the tensile force. Okay. And the distance between these two forces, whatever may be the distance between these two forces, it is called as, so this is called as lever arm Z. This is called as lever arm Z, the distance between these two forces. Then this compressive force is situated at a distance of from top. If you take this position, if you consider this distance, we have already seen this also. It is at a distance of 0.42 xu. It is at the distance of 0.42 xu. And what is the effective depth? So if we want to know the effective depth, then the effective depth is on this point. So the effective depth, if I show over here, then it is from this point up to this point. This is your effective depth. From this point to this point. And this effective depth, it is denoted by the letter D. This is your effective depth. Up to the reinforcement zone. So if I show it the same thing over here, then this D is the effective depth, and the distance is measured from this point to this point. This is your effective depth. And from this point to this point, that is your overall depth, from topmost point to last point at the bottom, that is capital D. So now if you see, this is D and this distance is 0.42 D, and if I now want to know the value of Z, then I can write over here Z is equal to what? It is D minus 0.42 x. This lever arm distance Z, it can be calculated as D minus 0.42 x, and the value of, now the value of these forces Cu and Tu. So what are the values of these forces Cu? How do we calculate the Cu? You are knowing the values Cu. How do we calculate Cu? So Cu is equal to, what is the answer? Cu is equal to, what is the value? 0.36 FCK B into XU. 0.36 FCK B into XU. This is the formula for Cu. This is called as compressive force. This is nothing but compressive force. And what is Tu? How do we calculate Tu? So Tu is equal to 0.87 Fy into AST, where this Tu is nothing but it is tensile force. This Tu is nothing but it is tensile force. This all we have seen previously in first lecture also. I am telling this you again to recall, because now we require this for the further calculations. Okay. So now after this now, depth of the neutral axis. How do we calculate the depth of the neutral axis? So to calculate the depth of the neutral axis, we assume that our total compressive force is equal to the tensile force. If we equate these two forces, compressive force is equal to tensile force, and we keep this term D. If we calculate the D, then we will get the equation as XU by D is equal to 0.87 FYAST divided by 0.36 FCK B into D. Okay. If we calculate the expression for XU, see, I will do here. Equate, instead of talking, I will write equate this compressive force to tensile force. Compressive force is equal to tensile force means what? Your section is balanced section. Okay, it is very neatly designed. So now it is equal to 0.36 FCK B into XU, which is equal to 0.87 Fy into AS. Now if I keep XU on this side, if I keep XU here, and if I send all the other terms on that side, then what will remain? 0.87 FYAST whole divided by, what will remain, it is 0.36 FCK into P. So this is the formula to calculate the XU. By using this, we can calculate the XU. Okay, XU means what? Depth of the neutral axis. XU max means what? Maximum depth of the neutral axis. Okay, so the next point now. So we will see the types of sections: over reinforced, under reinforced sections. So first of all, we will see under reinforced section. Okay. First of all, we will see here under under reinforced section. Under reinforced section. So what we can write about under reinforced section now? So under reinforced section, I can say that when x2 is less than x2 max. Okay. When we are looking for the definition of under reinforced section. So when what is the meaning of under reinforced section? When your XU, just a moment, when XU is less than XU max, okay, your depth of neutral axis is less than the maximum depth of neutral axis, or your bending moment is less than mu limiting. So when XU is less than XU max or mu is less than mu limiting, so this mu limiting, we call this mu limiting also MR, moment of resistance, is nothing but your limiting value of bending moment, that is the maximum value of bending moment, and this is the bending moment generated in that structure. So when XU is less than XU max or mu is less than mu limiting, then the section is then limiting, then the section is under reinforced section. Okay, so here I can write then the section is under reinforced section. Then the section is under reinforced section. Okay. Now in under reinforced section, now if you want to calculate the mu, if you want to calculate the mu, then it can be calculated as tu into z. Under reinforcement, what reinforcement is less. Okay. So AST is less, reinforcement is less. So for AST, reinforcement carries the tensile force. So to calculate the MU, you can use the formula TU into Z. Okay, here we have seen that. Here this is TU and this is Z. This distance. TU into Z is the moment. MU. MU you can calculate it as a TU into Z. Okay, so if I put the value over here, then what do we get? If I put the value, then mu is equal to what is tu? So tu just we have calculated 0.87 Fy into AST. This is the value of tu. And what is the value of z? It is d minus 0.42 x. This is the value of z. Okay, just above. You can see over here. Just above you can see over here, this is tu into z is nothing but mu when the section is under reinforced, and the value of z is d minus 0.42 x2, whereas this total distance is d, this much is 0.42 x2, so this remaining will be d minus 0.42 x2. So now after this we will see second type, that is balanced section. Second is the balanced section. So in the balance section now, when xu is equal to xu max, so whatever may be the depth of the neutral axis of the structure, which is equal to the maximum depth of the neutral axis, or your mu bending moment is equal to mu limiting. Okay, त्यालाच आपण MR म्हणतो, mu limiting, maximum limiting value of the bending moment or moment of a resistance. Then then the section then the section is what it is, balanced section. Then the section is known as balanced section. Okay. So in the balance section, you can calculate mu as Cu into Z. Okay. In the balance section now, if you want to calculate the mu, okay, if you want to calculate mu, then formula for mu it is Cu into Z. Formula for mu is Cu into Z. Just look the formula carefully where further mu is equal to Cu is nothing but 0.36 FCK B into XU instead of XU, as XU is equal to XU max, you can write here XU max. Okay, XU max. And what is the lever arm Z? It is D minus 0.42 XU max. D minus 0.42 XU max. So instead of XU, we put here the value of XU max, because XU is nothing but XU is equal to XU max. So after the balance section now, next is after balance section, next is over reinforced section. Over reinforced section. Okay. Over reinforced section means what? When when XU is greater than XU max, when XU is greater than XU max, or MU is greater than MU limiting moment of resistance, then the section is then the section then the section is known as over reinforced section. Then the section is known as over reinforced section. Okay. So generally we avoid to design the over reinforced sections. Okay. Generally we avoid to design over reinforced sections. Okay. Why we avoid to design the over reinforced sections? Because in the case of over reinforced sections, the failure of the structure is sudden. It doesn't give you any warning before the failure. Now what do you mean? If you design under reinforced section or if you design balance section, then before failure these sections give you some warning. Warning means what? You observe that the beam is cracked. Suppose the beam is there and it is under reinforced section. You design that beam as under reinforced section or balance section. Then before failing, that beam will give you the indication that it is going to fail. So you will observe the cracks along the diagonal. You will observe the cracks along the longitudinal axis, so that from that you can say that now this beam is going to be failed. So it gives some sign before failure. But in the case of this over reinforced section, the failure is sudden. It doesn't give you any sign. तुम्ही म्हणणार काल तर होतं की इथं आज कसं काय पडलं. Okay, so sometimes we heard the news that इथं काहीतरी आज भिंत पडली किंवा कुठेतरी कमान पडली, अशी काहीतरी न्यूज आपण ऐकतो कधी पेपरमध्ये किंवा काय. So that is nothing but that section is over reinforced section. When section is become over reinforced, it doesn't give you any sign before the failure and it fails suddenly. So therefore in practice, generally we avoid this over reinforced sections. We don't design the over reinforced sections. Now this is the introduction. which is needed for this chapter. Now we will see the numericals. Okay, so we have seen limit state, we have seen collapse, then we have seen limit state of collapse, what is the meaning, then after that singly reinforced section. Okay, what is the singly reinforced section? Then this table we have also seen in the IS code and here also, and this is the important diagram. Okay. This diagram is the important diagram which we have seen. CU, TU, Z, D, 0.52 XU, this strain 0.0035. This is combined axial and bending maximum strain. So what is CU's formula? TU's formula. Okay, and after that now here we have seen that what is under enforced section, and the formula for under enforced section TU into Z, and then balance section, formula for balance section, and the over enforced section. Generally we avoid to design over enforced section. Okay, and if in the exam you come across any over enforced section while designing, then assume this section as a balance section and then design the section. Okay. So now with this we will move further for the numericals. So we will take our first problem. So the problem number 1, we will take the first numerical. A beam of effective depth is given. It's provided with 4 bars of 18 mm diameter as a tensile steel. Find the depth of neutral axis. So you need to calculate the depth of neutral axis, means you need to calculate the value of XU. Okay, XU is nothing but depth of neutral axis. Find the ultimate moment of resistance. So you need to calculate what is the moment of resistance of the section. Now to calculate the moment of resistance, first you need to determine whether it is balanced section or under reinforced section. Okay, if under reinforced section is there, you can use TU into Z. If the balance section is there, you can use CU into Z formula. Okay, so in that way you need to approach this problem. So I will draw the diagram here what they have specified in the problem. So here the reinforcement is there 4 bars, 1, 2, 3, and this is 4. These 4 bars are provided, each of diameter 18 mm. Okay, so the diameter of this bar is 18 mm diameter. Diameter is 18 mm for these bars. Okay. So now the distance which is given, it is this is 250 mm wide. So this is 250. And they have not given us the overall depth. They said that effective depth means what, up to the center of this bar. Okay, so here may be the axis. This is the center line of the bars, and this depth it is given to us as 500. This is nothing but effective depth. This is nothing but small d is given to you. The value of small d is given to. Okay. So if I write over here given data, so b is equal to what? 250 mm. D is equal to 500 mm. Then FCK FCK is equal to 20 Newton per mm square, and Fy it is 250 Newton per mm square. The value of Fy is 250. It is 250. So now next, further, what they have given, area of steel is given to us. It is provided with 4 bars of 18 mm diameter. They have given us in the problem 4 bars of 18 mm diameter. This is the statement given in the problem. So here we can calculate area of steel. What is the area of steel now? How many bars are provided? 4 into diameter of each bar is 18. So 5 by 4 into 18 square. If you do this calculation, it works out to be 1017.87 mm square. So this is the value of area of steel, AST. Now to calculate the depth of neutral axis, here I can write to calculate depth of neutral axis. Assume assume the section assume the section is balanced section. Okay, what we have assumed, section is a balanced section. Now if the section is balanced, we can equate Cu is equal to what? Tu. Okay, so what is the value of Cu then? 0.36 FCK B into XU must be equal to, what is the value of Tu? 0.87 FY ES. This is the value of T. Now we want the depth of neutral axis, that is we want the value of XU. So we will keep XU on this side, and then we will send all the terms to the other side. So it will become 0.87 FYAST divided by 0.36 FCK B. Just now you need to put the values. Okay. Just we need to put the values. Now if we put the values over here, what we will get? XQ is equal to. Now if I put the values, what are the values? 0.87 is as it is. Okay. So 0.87 is as it is. 0.87 into FY FE250 is given 250 into AST किती काढलं होतं आपण? AST was 1017.87. We already calculated AST above, and whole divided by, it is 0.36 into HCK is 20 into B is 250 width of the section. Therefore X2 is equal to, now do the calculation, let me know the value of X2. What is the value? 122.99 mm. This is the value for XU. The value for XU. Okay. Now first job is over. What they have asked us, find the depth of neutral axis. So we have got the depth of neutral axis. 122.99 mm is the depth of neutral axis. Okay. So first thing is known to us. Then second, ultimate moment of resistance. Now to calculate the ultimate moment of resistance, here we are having these two formulas, mu equal to T into Z and mu equal to Q into Z. But the important thing is, we need to determine that this section is whether balanced section or under reinforced section or over reinforced section. Okay. So our first job is to compare that, to see that whether the section is over reinforced or section is balanced or the section is under reinforced. So for that purpose now, we are having the value of XU now. So if we calculate XU max, then by comparing XU and XU max, we can say that the section is under reinforced, over reinforced or balanced section. So our next step is to calculate the value of XU max. Okay. So I will write here, calculate calculate XU max. Okay. Calculate XU max. Now to calculate XU max, what we will do? We will go to page number 70, clause number 38.1. Clause number 38.1, page number 70. Okay. So from this I can write XU max upon the must be equal to 0.53. This I have already shown you at the start of the lecture in IS code also. XU max is equal to D is equal to 0.53. Now if you move further, then you can write over here XU max is equal to 0.53D, which is equal to 0.53 into 500, which is again equal to, what is the value of XU max then? 265 mm. That value works out to be 265 mm. Now compare XU and XU max. Now here compare XU and XU max. What is the value of XU max? XU max is 265. And what is the value of XU? The value of XU is here, the value of XU. The value of XU is 122.99. Okay. And the value of XU max, it is 265 mm. This is the value of XU max. Now you can see who is greater, who is less. So XU is less than XU max. Okay, in this case over here, XU is less than XU max. So I will write XU is less than XU max. And we know that when XU is less than XU max, then which type of section is there? Therefore, it is under reinforced section. Therefore, it is under the reinforced section. Okay. Now, if the section is under reinforced, you can use the formula to calculate mu. Mu is equal to, if under reinforced section is there, your formula is Tu into Z. So mu is equal to, what is the formula for Tu? 0.87 Fy Ast in bracket B minus 0.42 x. This is the formula. Just put the values now. So the mu is equal to, we need to put the values. So 0.87 into 250 into AST, it was 1017 point something 87 into B effective depth was 500 minus 0.42 into XQ was 122.99. If you solve this problem, then you will get mu is equal to, what is the value? It is 99.25 into 10 raised to 6 Newton mm. Okay, this is nothing but 99.25 kilo Newton meter. 99.25 kilo Newton meter. So this is the value of mu. Sorry. So again, if you see the problem, we have calculated each and everything from the problem. They have given a rectangular section, 4 bars of 18 mm diameter. Then they told us here, they told us to calculate the depth of neutral axis and then also moment of resistance. So we have calculated all the things. How do we calculate? Here first we calculate XU. After that we calculate the value of XU max. If we compare both the values, we got that the section is under reinforced. And for the under reinforced section, what is the formula? It is Tu into Z. We put all the values over there in this formula and we got this value mu is equal to 99.25 kilonewton meter. Okay, 99.25 kilonewton meter is the answer. Now we will move to the next problem. So with me you also write down the problem. Next problem. A beam of rectangular section, second, a beam of a beam of a rectangular section 250 mm wide, 250 mm wide and 450 mm effective depth and 450 mm effective depth is provided with 4 bars of 16 mm, 4 bars of 16 mm diameter as a tension reinforcement, as a tension reinforcement. Full stop. Find the depth of neutral axis. Find.
सर आवाज क्लिअर येत नाही.
हा काय झालं?
आवाज क्लिअर येत नाही.
आता येतोय का?
क्लिअर आवाज येत नाही. हा आता येतोय.
यायला लागला का? Okay.
हा हा
Find the depth. Find the depth of neutral axis and ultimate ultimate moment of resistance. Ultimate moment of resistance. Okay. So this is the given problem again. Same on the same line the problem is there. A beam of rectangular section 250 mm wide and 450 mm effective depth is provided with 4 bars of 16 mm diameter as a tension reinforcement. Find the depth of neutral axis and ultimate moment of resistance. So here I will give you the 5 minutes. You try to solve this problem and come with the answer. Solve it now. So for this problem, B is 250. You solve the problem and you tell me the value of XU. B is equal to 450 mm. AST, area of steel which you have calculated, that AST is equal to 4 into 5 by 4 into 16 square, which is equal to 804.44 mm square. Okay, now to calculate the value of XU, what we do? We assume balance section. So if you assume balance section, then Cu must be equal to T. Therefore, is 0.36 FCK B into Xu must be equal to 0.87 Fy AS. So if you just put the values, you will get the answer. So Xu is equal to what? It is 0.87 Fy AST whole divided by, it is 0.36 FCK B. Okay. Now you just put the values, you will get the answers. So XU is equal to, it is 0.87 into Fy. What is the value of Fy? It is 250 into area of steel 804.24 whole divided by 0.36 FCK. Sorry, the value of FCK we need to put. No? The value of FCK is 20 into B. The value of B is 250. So from this you will get the value of XU. Let me know the value of XU. किती आली value? Anybody who has solved this? 97 point
19.179.
uh, 9 97.179. Correct ka? Have you got this answer? 97.1.
Correct, sir.
Okay. 179 mm. So this is the value of XU. Now what will be our next step? आता हा एक पार्ट कंप्लीट झाला इथपर्यंत. इथं तुम्ही एक पार्ट कंप्लीट केला. ते त्यांनी काय सांगितलं प्रॉब्लेम मध्ये फाइंड द डेप्थ ऑफ न्यूट्रल ऍक्सिस. सो अप टू दिस पॉइंट यू गॉट द डेप्थ ऑफ न्यूट्रल ऍक्सिस. What they have given you further? Ultimate moment of resistance. We need to calculate ultimate moment of resistance. So to calculate the ultimate moment of resistance, we need to know that the section is under reinforced section, balance section or over reinforced section. Initially we assume that it is balance section. So now we need to do this, and for that you need the value of XU max. Okay. So to calculate the value of XU max, what we do now? We use clause number 38.1, page number 70, and use the ratio XU max by D. Okay, so here I will write calculate XU max. कुठनं calculate करणार? Clause number 38.1, page number 70. So from that you will get XU max upon D is equal to 0.53. Therefore, XU max is equal to 0.53 D. XU max is equal to 153 times D. So here we can write XU max is equal to, it is XU max is equal to 0.53 into, it is 450. What is the answer? What is the value of XU max?
238.5. 238.5, sir.
Okay, 238.5. Good. So this is the value of XU max. Now compare the values. XU is 97.179 and XU max is 238.5. Who is greater? XU max is greater. XU is less. So here we can write in this problem here XU is less than XU max. And if XU is less than XU max, what type of section it is? Then the section, this indicates that it is under reinforced section. Okay. It is under reinforced section. So now if the under reinforced section is there, what is the formula to calculate mu? So the formula to calculate mu is equal to Tu into Z. This is the formula for under reinforced section. So mu is equal to Tu. Tu is 0.87 Fy AST in bracket D minus 0.42 XU. So this is the mu formula for mu. Now put the values. Mu is equal to 0.87 into Fy is 250 into AST What was our area of steel? 804. 804.24 into D. What is the depth? It is 450 minus 0.42 into XU. What is the value of XU? XU I think 97.179 is the value of XU. If you put all these values, you will get the value of MU. Let me know the value of MU. Answer Sanga.
71.57.
71 point. Repeat करा 71.57.
57.
Okay. The answer is 71.
57.
काय झालं? Is it the right answer?
Yes. Yes, sir.
So
I
71.57
remember.
kilonewton meter.
Mhm.
This is the answer. Now again, after this we will move to the next problem again. This is now our problem number 3rd. Okay. We will move to problem number 3rd. So take down the next problem. Problem number 3. Here a singly reinforced beam, a singly reinforced beam 300 by 500 mm, 300 by 500 mm with a clear cover, with a clear cover, with a clear cover of 40 mm is reinforced is reinforced with with 4 bars of 20 mm diameter, 20 mm diameter. Find the flexural strength, find the flexural strength and UDL, find the flexural strength, flexural strength. Okay, just a moment. First, you need to calculate the XU, and for that, you need to calculate the area of steel first. So we will calculate the area of steel. I will write here given data first. So B is equal to what? B is equal to 250 mm. D is equal to what? D is 500 mm. Okay. Now what is the value of small d then? What is the value of small d? Small d is equal to overall depth minus clear cover दिलेले, clear cover is 40 minus half of bar diameter 20 by 2. So this must be equal to 500 minus 40. किती येते? It is 442. Am I right? It is 442. Now again, AST, area of steel. What is AST? 4 bars of 20 mm diameter. So 4 into pi by 4 into 20 square. So if you do this, what is the value? It is
Sir.
what happened?
Sir, DC value 458.
DC value?
DC value 458, sir.
Loudly, I am not getting your voice.
450.
450 येते का?
450.
Okay.
Ah.
Okay. 40 minus 10, 50, 500 minus 50, 450. Correct. So the value, right. Now AST. What is the value of AST? AST ची व्हॅल्यू काय आली? 804 येते का?
1256.6.
It is 1 2
1256.6.
पुढं
63. 63.63.
0.63. So 1256.63 mm square. This is the area of steel. Correct? Okay. Now after the calculation of area of steel, you assume the section is balanced section. Okay, assume it is balanced section and equate Cu is equal to Tu. Equate Cu equal to Tu. Then what do you get? 0.36 FCK B into XU must be equal to 0.87 Fy AST. Okay. Now from this you will get the value of XU. Just put all the values. So if you reshuffle the formula for XU, then what you will get? XU is equal to 0.87 Fy AST whole divided by 0.36 FCK into B. So if you put the values, it is 0.87 0.87 into Fy किती आहे 500 आहे वाटतं 500 into 1256.63 whole divided by 0.36 into FCK is 25 into B. What is the width of the section given? I think it is 250. 250. So now from this you will get the value of XU. I don't have answer. Let me know the value XU. This is unsolved problem. What is the answer? XU?
202.45.
Okay. So it is 202.45.
Sir.
What happened?
Width is 300, sir. Sir, the क्या है 300 आहे सर.
B 300 आहे का? Correct. ठीक आहे. Okay. So this value is 300. It is given in the problem. It is 300 by 500. So it is 300. So now after the calculation of XU, what we do? We calculate XU max. Okay. So next is calculate XU max. Calculate XU max. So now to calculate XU max, what we do? We use clause number 38.1, page number 70. Okay. From that we will get XU max is equal to, now what is the grade of steel? It is 500 now. So for 500 it is 0.46 D I think. XU max is equal to, for the grade of 500, what is the value for 500? 0.46 is the right answer. So XU max is equal to, if you put the values over here, 0.46 into it is D is 450, then the value works out to be What is the value? 207. करेक्ट. बरोबर आहे ना माझं? चेक करा बरं का कॅल्क्युलेशन. So XU max is equal to, I think so, 207. So now here compare again the values of XU and XU max. 202 आहे XU, 207 आहे XU max. म्हणजे greater कोण आहे? XU max greater आहे. So here again we can write here XU is less than XU max. Therefore the section is under reinforced. The section is under reinforced. So if the section is under reinforced, then mu is equal to, it is tu into z. Mu is equal to tu into z. So now mu is equal to tu 0.87 fy ast in bracket d minus 0.42 xu. So now again put the values. So mu is equal to, it is 0.87 into fy. Fy is 500 into ast. Area of steel किती आला होता? 1256.63 in bracket 450 minus 0.42 into xu. Value of xu is 202.4 something. So from this we will get the value of mu. हाँ.
Sir, 199.5.
हाँ. What is that?
199.5.
199.199.5. Okay, 199.50 kilonewton meter. Okay, this is the value of mu. Now after mu, what we will do now? We want to calculate the safe load. आता ह्याच्या पुढे जाऊन एक तुम्हाला विचारलंय की what is the safe load or safe UDL. So we equate this mu, but we know what we know for simply supported beam. What is condition given in the problem? They have asked you. Okay, it's a problem. Might be it is not loading due to the connection. Okay, but in the problem it is given that the beam is simply supported and we have to calculate the safe load. So if the beam is simply supported, if this type of beam is there, simply supported beam is there, okay, and UDL is acting on the beam, and we want to calculate this value W kilonewton per meter. Okay, and here the span they have given it as a 5 meter. So the maximum bending moment for this beam will be in this way. And this maximum ordinate, what is this maximum ordinate? It is WL square by 8. So equate the maximum bending moment to WL square by 8. Okay, so here equating, so we will equating mu is equal to WL square by 8. They have given in the problem the beam is simply supported, that is why we are equating to WL square by 8. If in the problem they mention that the beam is cantilever, then you have to use your WL square by 2. Remember that depending upon the boundary condition you need to use the formula. So here it is 199.50 kilonewton meter, which must be equal to W as it is into span, it is given in meter, it is 5 square divided by 8. If you reshuffle the terms, you will get the value of W. Okay, so it
63.84.
is 63.84 kilonewton per meter. So this is our, what we can say, ultimate load. Okay, because this is the ultimate moment of resistance, so this is our ultimate load. So to calculate the safe load, we should divide this by factor of safety, so we will get the safe load. So to calculate the safe load is equal to working load divided by factor of safety. 84 divided by factor of safety is 1.5. In the problem they have asked us for the safe load. So safe load is equal to, what is the answer? It is I think 42 point something, no? 56 kilometer. 42.56,
156.
right answer. Okay.
Yes, sir.
So now we have solved three problems based on the third unit. All the problems are very easy. These types of problem can be asked in the exam to calculate the moment of resistance or to calculate the safe load. Many cases instead of UDL, they may have also give point load acting on the beam, and they may told you that calculate moment of resistance as well as point load acting on the beam. So in tomorrow's lecture or whenever our next lecture is there, in that lecture we will take these problems instead of this UDL. Okay, now what we have calculated here, the UDL. Instead of this UDL, when the point load is acting on the beam, then how to calculate the moment of resistance and the safe point load. That we will take in the next lecture. Okay.